at University of Michigan, Ann Arbor. He is member of Academia Europea, ACM, IEEE, and many other professional societies. He was founder of computer architecture group at Microsoft Research from 2006 to 2009, and he was a different research position in Intel, AMD, Google, and so on. He was recipient of many awards, but also he had many important international projects financed by Huawei, IEEE, and National Science Foundation. Also, Professor Mutlu has impressive academic citation record. I'm giving you the floor. Please, Professor Mutlu, deliver your lecture on say, energy efficiency.
Thank you. Thank you very much. Yeah, thank you very much for the very kind introduction. Is this working? Yeah. Okay. I don't want it to be too loud also. And thank you very much for the kind invitation to the Academy. I'm happy to be here. And I'll talk about energy efficiency. I didn't title it energy efficiency because it's going to, even though it's going to be mainly about energy efficiency, but we're going to talk about memory-centric computing. And I understand that we have about 40, 45 minutes. I have many more slides than that, but we don't need to cover it. Hopefully, I'll give you a perspective of what is limiting energy efficiency and also performance, and also security and reliability in modern computing systems today. And I think that's in the title, that's in memory over here. Okay, so if you look at computing today, computing is bottlenecked by data, and many important workloads and important problems that we want to solve are data intensive. We need rapid and efficient processing of large amounts of data. And on top of this, data is increasing. We can generate more data than we can process in many fields today, many areas. I'm going to give you some examples of this very soon. And we actually need to perform more sophisticated analyses on more data. So essentially, we're greedy. We want more and more data, and we want to do more and more of that data. Of course, many of you are familiar with neural networks, probably machine learning. This is clearly an area where demand for data is growing. This is a presentation from the chief architect of the Cerebras systems. These people are building chips that are this big. These are wafer scale chips. And the reason they're building the chips that are this big is because of what they show over here. Basically, over time, the memory requirement of neural networks is growing exponentially, as well as the compute requirements of neural networks is growing exponentially. Today, everybody's talking about ChatGPT and its variants, as you know, probably, and it's growing exponentially. Essentially, we don't have systems that can deal with this growth today. And this is one example of the data growth that I mentioned. But it's not only neural networks. There are many, many other workloads that are important in our lives: databases, graph analytics, data centers. They're all bottlenecked by data in the end. So data is a big bottleneck in terms of performance energy. And if you look at the mobile end, on my cell phone, I use these workloads, for example, but you may be using similar workloads. You're again bottlenecked by data in these workloads. And I'm going to give you some data that we have actually collected together with our industrial partners to see how big this bottleneck is. But we'll get to that. Before, I want to talk a little bit more about genomics. This is an area that's exploding today. Essentially today, because of the success of the sequencing technologies, you can sequence a genome, RNA or DNA or proteins going into the future very efficiently. As a result, people have been sequencing genomes, and this graph I like pointing out because what this shows is the cost of sequencing versus the cost of a transistor. Essentially, cost of sequencing has been reducing exponentially, as you can see with this curve. And this is the introduction of new technology, another introduction of new technology over here. And if you look at this other linear, well, it's exponential, but it's shown linearly here because it's a log scale, as you can see. This is Moore's law. Basically, the cost of a transistor is reducing much more slowly than the cost of sequencing genomes. What does this mean? We need to process this genome to really understand what's going on. And you cannot do it just by adding more transistors because you're not actually scaling as well. So this is why I think genomics is an area that's very interesting, clearly, because there's a lot of applications. You need to, these sequencing machines are great, but you do need to do a lot of data analysis after that so that you can reach scientific discoveries and medical advancements. Essentially, this is an area where data is a huge performance energy bottleneck. And I'm going to give you some numbers over here, hopefully, if we have time as well. But just to motivate, I'm giving another talk on this topic this afternoon at 4 p.m. at the university, I believe. But there's a lot of interesting things over here in genome analysis. COVID-19 pandemic showed us a small part of it, but we need a lot faster and efficient genome analysis. Here, energy efficiency is extremely important, in my opinion, because we want these mobile devices, not these computers. We want very small mobile devices so that we can sequence genomes and understand what's going on. And these are actually some of the mobile devices that we have today. This is an Oxford nanopore machine. It does nanopore sequencing. It's one of the new technologies, relatively new. And this is a great data generator. You can actually buy this machine for $1,000 or so, and you can sequence your own genome. You can actually build this infrastructure. It's not that difficult. Actually, I recently seen a lot of news about a high school student building his own infrastructure with this and sequencing fish genomes, for example. It's fascinating. I think it has enabled a lot of innovation from very young people also. They can do it. The unfortunate part of this machine is it's a great data generator, but it has no capability of analyzing data. Basically, if you want to analyze the data that's produced by this machine, you need to move it somewhere. If you're lucky to a laptop, usually that's not enough. You need to move it to a data center. So you actually cause a lot of data movements all over the world to analyze the data that's generated by these machines. And this is what this talk is about. I'm not going to go into maybe a lot of detail because we don't have a whole lot of time. But the key is we're causing a lot of data movement in our system at the macro scale as well as the micro scale. I'm going to give you more data on that. So basically, this is a data generator. Let me give you a bigger picture. So this is another genomic sequencer. This is much more powerful, as you can see. It's much more costly. You need to probably pay actually close to $1 million to actually get this in the larger scale. But it's a bigger data generator. It's much more expensive data generator. But it's similar to a collection of these. So what we're doing today is we have very special purpose machines for data generation in genomics. We're moving the data, a lot of data movements, and having general purpose machines for data analysis. So this is inefficient because this is much more capable than this machine over here for analysis, and also we cause a lot of data movements. And again, it's not a problem just with genomics, unfortunately. Genomics is interesting because these machines are becoming extremely powerful, but we replace this machine with a video camera, with a collection of video cameras all over the world. That's what's happening today, and we have the same problem basically. Video camera is a very specialized machine for ingesting, let's say, visual input. But our general purpose machines are overwhelmed by that. Replace this machine with a distributed system of people clicking on the web. That's a huge data generator. We have the same problem. These are specialized systems that are generating data. Our general purpose systems are suffering essentially because we're moving a lot of data as well as we're not specialized for processing data. So essentially, we have this picture today. That's why we're having a huge, in my opinion, energy efficiency and performance problem. I believe we need to eliminate this data movement as much as possible. And also, we need to make these systems match the specialization of these systems, meaning that these cannot be general purpose. These need to be more specialized to what's happening in the application. So that's the gist of my talk, basically, going into the future. That's what a data-centric or memory-centric system is. We want to do the processing as much as possible in a single system, if we can do it. Okay, I will not go into more genomics. We have been writing a lot of papers on this topic. I'm not going to bore you with all of these papers and the details of it. If you're interested, you can certainly look at them. This is a more recent one that's coming up in July, for example. It's an invited paper that talks about some of the issues that we see in accelerating genome analysis through the co-design of the software and the hardware across the system. But we've also written past papers. If you're interested, you can take a look at them in both architecture and biology journals, as you can see over here. Let me give you one example of what you can achieve today if you actually specialize your system to the application. I'm not going to go into the technical details of this, but today we have FPGAs, and we actually have very capable FPGAs. We did this work together with IEDM. We have a very powerful general purpose CPU, and connected to it, you can have an FPGA board. This is a configurable computer, essentially. And we have high bandwidth memory attached to it. So basically, you have logic that you can reconfigure that is high bandwidth, connected at high bandwidth to memory. So you can think of this as a near memory accelerator, and it is. And what we did was we took two important applications, weather modeling, the Cosmo weather model, and genome analysis, a part of the genome analysis application. And we offloaded some of the key parts of the workload, and we configured the logic such that it can be accelerated, and such that we can also take advantage of being near memory. So the data doesn't need to move all the way to the general purpose CPU, but the data stays here, and it gets processed by specialized logic that's specialized for the application. And if you do that, again, it requires a lot of work, of course. The programmer needs to do this. They need to understand the domain, etc. These are the key results. After doing all of that work, you get significant performance improvements, 5 to 27x. And you get significant energy efficiency improvements, more than performance improvements, in fact, up to 133x. These are 1 to 2 orders of magnitude, as you can see. And this is what you can do today. Essentially, with this sort of system, with this sort of near memory acceleration, specialized, you can get a lot higher performance and energy efficiency. There used to be a time where we had this trade-off, right? We wanted to improve performance, but we said, okay, you can increase energy. I think we're past that time. We want higher performance and lower energy at the same time. That's why this sort of acceleration is very important, in my opinion. Okay, so I can bore you with more stuff, but these are some of the cutting-edge works that are going on in the field. We're looking at approximate string matching acceleration, again, with similar ideas, but you need to really understand the high-level software algorithm so that you can accelerate it in hardware. And we have, as I mentioned, there's work on both bioinformatics side as well as the architecture side. Okay, I'm going to get back to this because data set sizes are growing. You may say that, okay, memory is not enough. Memory is small, right? It's terabytes. I'm talking about terabytes is small today. What about petabytes, exabytes? Well, then we need to move to storage. Storage is extremely big today. I mean, more storage. So you actually need to push the processing to the storage. I'm going to generalize it a little bit more when we go forward. Okay, I can keep going through this, but we don't have time. So I think the future is actually very interesting. Future is about these accelerators, but also making them portable. So we have multiple projects going on how to make them portable and efficient. In fact, one of them is funded by the European Union Horizon project. We have a big one that is essentially, it's called BioPim, and the idea is to really build these devices as much as possible. I'm going to maybe mention that later. Okay, let me skip the genome analysis part. There's a lot I can talk about. I love this field. I love this area. And we actually do a lot of courses on this topic. We recently organized a bioarchitect acceleration of bioinformatics workloads in the ReTHINking conference, which is a major computational biology conference, which was held in Istanbul in April. If you're interested, you can learn a lot more information about this. I think it's fascinating. But this is another application. Right? We have so many of these applications. We started with machine learning. We said other data intensive applications. We said genomics. All of these have in common that they have data and they're overwhelming our modern machines. Now I'm going to give you the machine perspective. Basically, we design machines with storage and memory, communication and computation, and all of them are being overwhelmed by these applications. And also data is greatly impacting robustness, energy, performance, and cost. We're going to talk about these at varying levels of detail. So if you go back to the fundamentals of electronic computers were set in 1940s. And this is von Neumann. He's one of the pioneers, clearly. And if you want to build a computing system, you need to have computation, communication, and storage. And we've been building systems like this. Unfortunately, we've been heavily focusing on the computing unit. And in my opinion, mostly forgetting the rest of the system. The rest of the system is more important, perhaps, but we're very processor-centric today, for various reasons we can talk about. This is my picture from 2008. I actually wrote my first National Science Foundation proposal while I was at Carnegie Mellon University. And I used this picture to motivate what we were doing. Essentially, this picture is very similar today, although things are changing a little bit, as I will tell you. But essentially, if you look at a modern system today, you have cores. These are essentially processing units. And what I showed you here, computing units, if you think about it. Everything else in a chip is dedicated for data movement and storage. Caches, interconnects, other caches, other interconnects, memory controllers, other interconnects, memory, other interconnects, storage, other interconnects. So if you look at a single node, I'm talking about a single computing chip, Intel chip, for example, most of the system is dedicated to storing and moving data, more than 95% actually, if you include the storage. Now, unfortunately, the system is still bounded by memory and storage. That's just looking at these facts should make us think maybe we're doing something wrong in our systems. We're dedicating almost all of our resources to memory and storage, yet we're still bottlenecked by memory and storage. I'm going to quantify these soon. Okay, if you don't like my picture, this is a real picture from AMD. This is one of the cutting edge chips. If you look at this green box, that's essentially L3 caches, part of L3 caches. This is memory. They cannot do computation. Computation is restricted to these cores over here. So this is global memory interconnect. So most of the chip is essentially there to serve data into the chip. Computation is a very small fraction of the chip. And there's a reason for this. We're building our systems in the wrong way, in my opinion. Okay, and then we're adding more chips. So this is this chip. On top of this, we're adding another chip just for memory, cache, essentially. This is very nice technology from AMD, 3D stacking, so you can 3D stack chips. But it shows the mindset. This, if you don't like AMD, this is IEDM. Essentially the same thing. Most of the chip is dedicated to caches, and I could keep going, giving you examples from different systems. They're all the same, essentially. Let me give you another example I like. This is a system on chip, Apple's flagship system. You can see that this is the compute chip. There's a lot of SRAM. We're going to look back into this later. Most of the system is really DRAM, main memory, and there's a darkness over here, which is storage. So again, most of the system is dedicated to storage and data. Now, let me give you some data. So we examined these applications. Clearly, these applications are used by many people in the world. We worked together with Google over the course of several years, and we wrote this paper in 2018. And this paper basically showed that on those applications, most of the system energy is spent on data movement, more than 60%. And these were data sets that were not extremely large at the time. So we repeated a similar study for the neural network accelerators. Google designed these TPUs, tensor processing units, essentially to accelerate machine learning. They actually use these in their data centers as well as phones. And we looked at their proprietary machine learning models. And we found out that the problem is even worse. Basically, more than 90% of the total system energy is spent on memory in large machine learning models. These are transformers, long short-term memories, and large language models going into the future. Essentially, most of the system energy is spent on memory. And that's why memory is equal to energy today, in my opinion. Anyway, if feel free to ask questions during the talk also, but we can also get to the end. And feel free to stop me if I'm running out of time, because I can go on for a long time. Now, before I go into a little bit more detail on what we are doing, I don't want to go into a whole lot of deep technical detail, but I want to motivate things a little bit more. But I think we need to design intelligent architectures going into the future. Our architectures are not very intelligent because we're not handling data. So what does it mean to be intelligent? I think we should ensure that data doesn't overwhelm the components we design. This requires us to design intelligent algorithms, architectures, thinking across the stack. I'll show you a picture of it. But we also need to design our components to be intelligent, meaning if you design a processor component or a software component, it should learn from its past. Today, the components are designed in a very human-driven manner, meaning a designer sits, thinks about what the component should do, and comes up with some heuristics saying that this component should behave this way. Meaning that the component is not able to learn. This is very different from humans. As a human, very quickly, I figure out, based on the interaction with the environment, what I should do and what I should not do, right? I put my hand on a hot stove, and I get burnt, and I figure out that I don't want to do that again. So nobody tells me the heuristic. So I think going forward, we need to do similar things in our systems, meaning they need to be more experienced in learning-driven systems. The decisions need to be more longer term. So we are looking a lot into, for example, how to design the hardware itself, such that over time it figures out what to do by itself, as opposed to a designer dictating what it should do. So I think this is going to be very important in the future. I'm not going to talk a lot about that, but it's extremely important for energy efficiency as well. And the third direction over here is today's systems don't know much about the data, even though data is extremely important. When actually you express the data, you don't know the characteristics of the data. They don't get communicated to the underlying architecture. I'll pick one example. For example, in many cases, so what kind of characteristics does data have? Data has security properties, privacy properties. It has approximability properties, error tolerance properties, reliability properties, locality properties, so lots of different properties. These properties never get expressed to the underlying hardware in general purpose systems, especially. As a result, the decision of the hardware or sometimes the software actually makes is not considering the properties of the data. So, for example, if I knew that I could tolerate a lot of errors on a piece of data, I could actually process that data a lot more energy efficiently by ignoring some things in the computation. Right? But we don't do that today. So I think going forward, we need to be much more data characteristic aware. So this brings us to this, let's say, research vision that we have. We want to make the system much more data-centric as opposed to processor-centric. I'm going to talk more about that. We want to make the system much more experience or data-driven as opposed to designer-dictated. And finally, we want to make the systems make data characteristic aware decisions as opposed to component-based myopic decisions. Again, we don't have time to talk about the second and third one, but these are also extremely important for efficiency going into the future. So we call this vision as a data-centric, data-driven, and data-aware architectures. And this requires thinking across the stack because your algorithm may need to change for this purpose, and your devices also may need to change, and they may need to be co-designed. And hopefully, I'll get a chance to give you some examples of this. Okay, so if you're interested in this vision, we've been writing papers about. Let me jump into the first part of it, which is what does it mean to be data-centric? Even if you pick the first one, data-centric, it opens up a whole world, in my opinion. So these are the properties that I could come up with. I'm not going to go into all of them, but we need to enable low latency, low energy data access, low cost data storage and processing, and we need to manage data intelligently. But I'm going to focus on especially the first one, as I alluded to. We should really be processing data where it resides or where it makes sense, as opposed to bringing the data up into a computer, a particular piece of a computer, and requiring it to be processed there. So let's jump into that. I call it where it makes sense. Essentially, if the data makes sense to be processed in the sensors, for example, in that camera or in that projector, it should be processed over there. So if you look at this SOC that we looked at earlier, we have a lot of places to process data. We could process in the sensors, storage, DRAM, in the memory structures over here, but we're restricting ourselves to compute units right here. So this is not a new idea. This is an old idea. A lot of good ideas were proposed in the 1960s, and these are beautiful papers that were written by some visionaries in the field. If you're interested, Harold Stone has a paper also on this topic. Essentially, this idea has been proposed. Put logic and memory together as much as possible. But it has not been enabled, let's say. Today, we're in a different world, in my opinion. And today, we need to think differently. Let me give you why this is interesting today. So essentially, today, we have nowhere to escape, in my opinion. We're having huge problems with the memory technology. I will cover this very quickly. But we also have huge problems with the application of the systems. And then our designs are squeezed in the middle. We're nowhere to escape. What does this first one mean? So technology scaling is not going well. We have a lot of reliability issues like RowHammer, which I will briefly talk about. Actually, I have another lecture tomorrow on hardware security where I'll talk about this in more detail. So many of these technology scaling issues demand intelligence in memory, meaning more computation in memory. And this is already happening. I'm going to give you examples from real industry showing that to solve these problems, they're adding more intelligence inside the memory side. They were very resistant against this because this is expensive, of course, but now they're doing it because they have to do it. And the second is huge demand from application systems. We have a huge bottleneck, energy and power, huge bottlenecks, data energy dominance compute. We're going to look at this. And we want performance, energy, and sustainability all at the same time. And we can improve all metrics by minimizing data movement, as I will show you. So essentially, designs today are squeezed in the middle. We have nowhere to escape. So let's take a look at this. As a result, things are happening today. So if I was giving this talk, let's say 4 years ago, maybe 5 years ago, you wouldn't see a lot of these. So we have basically 3D stack memory technologies today. You have memory and logic underneath, so you can actually put computation. Industry is experimenting with new things. In fact, this UpMem startup company in 2019 introduced a DRAM chip that actually has processing logic inside it also. This was considered nobody should do it in the past. Today, people are doing it. Okay, you can say UpMem is a startup. I ignore them. But Samsung, SK Hynix, these are two of the top DRAM manufacturers. There are only 3 DRAM manufacturers today. These are main memory manufacturers. They hold more than 90% of the market, Micron also, including 95% of the market. They've been putting logic inside their DRAM chips so that they can accelerate important applications like neural networks. This is another module from Samsung and Facebook, where they actually put processing inside this buffer chip and lots of memory, as you can see over here, to accelerate recommendation systems. And companies like Alibaba have been designing their own memory chips to actually accelerate recommendation. So this is happening today. And before I had all the elements of the talk without these pictures, now I have these pictures, let's say, for the last several years. And I believe this is going to happen more. Okay. And there are many other experimental chips and startups that are not shown in this picture, of course. Okay, so if you're interested, I'm happy to talk about it, but let me give you the technology perspective of it. So we've been looking at memory technology for some time. This is a paper, or this is an invited talk that we gave at this industry workshop. And we argued that technology scaling is not going well. We should design controllers to be much more intelligent. And we said that this is mainly motivated by a lot of issues, but reliability is one of them. So while we were doing this research, we also discovered that in memory chips that is used in all computers today, you can predictably induce errors. Meaning by doing certain actions to the memory chip at the program level, you can get bit flips. Meaning if you store data value 1, it becomes 0, for example. This should not happen, clearly. You should really have reliable data storage. But this is known as RowHammer right now. And again, I'll talk about this in a later lecture, but this is important for many things. So the reason, let me give you the reason going into a little bit more detail. Basically, memory consists of rows of cells. This you can consider a bank of memory. You can actually activate a row to read data from one row, you apply high voltage to that row. Now, if you want to read some other row, you apply low voltage to this row, close this row. Now, you can do this repeatedly using a high-level program. Activate low voltage to high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, high voltage. This is called the hammering part. And essentially, once you hammer this row this way, you get bit flips, meaning corrupt data in adjacent rows. This is not supposed to happen, but this is happening because cells are too close to each other and cells are too small. As a result, the perturbation that you cause on this word line because of the changing of the voltage rapidly leads to charge to be leaked from cells around it. And this caused a reliability problem and also a security problem. So there are 3 major DRAM manufacturers, as I said, that are producing most of the world's memory, and all of their chips are vulnerable to this effect. And again, I will not go into detail, but it's also security vulnerability. Later works show that by exploiting these bit flips, someone can take over your system completely. And you can see some article that says, forget software, now hackers are exploiting physics. I like this because this is really about the physical nature of things. Again, I will not go into detail on this one. There's things that are happening right now. You can read papers about it. And we have a paper coming up at ISCA showing that the problem is actually much, much worse than what people thought before. But let me, I mean, you can certainly look at lectures, etc. But let me give you, why am I telling you this? Why I'm telling you this because this sort of problem can be solved by having more intelligence on the memory system. You need to have an intelligent memory controller that detects this access pattern. Somebody is hammering your rows. This requires hardware cost and some intelligence. And we argued from the very beginning, from 2012 or 2011, when we were doing this research, that we should have these intelligent controllers. And finally, they're happening. This is from the flagship circuits conference in 2023 from SK Hynix, the second major DRAM manufacturer. They basically wrote a paper, and the paper has RowHammer in the title. Well, somewhere I guess, somewhere over here, they talk about RowHammer essentially. But basically, they solved. They have a solution to the RowHammer, and they admit the problem, as you can see. That's also a big thing. So you can see that they talk about RowHammer. So how did they solve the problem? They basically modified the DRAM chip. So they modified the DRAM chip so that they can have these counters in the DRAM and some controllers, some intelligence in the memory. Essentially, what we've been advocating, it's very similar to some of the solutions that we have developed in the past. And it's not just SK Hynix. There's also Samsung. They've also actually written papers. So this intelligence in memory is happening, and on the DRAM manufacturer side, as you can see, and finally, they're also admitting it, as you can see. So this is a great idea. So you may say, okay, DRAM is an old technology. It was invented in 1960s. It's going to go away. Perhaps we've been working on that also. Basically, there are other technologies that are quite interesting, like phase change memory. Unfortunately, there is no technology that doesn't require an intelligent controller. Phase change memory requires an intelligent controller much, much more than DRAM because it has some other reliability issues like endurance. Whenever you write to a cell, the cell degrades. So you cannot do so many writes to a cell, just like flash memory, just like the SSDs we have today. So unfortunately, we have nowhere to escape, in my opinion, unless someone comes up with a fundamentally different memory technology that doesn't have these problems. And I believe that that doesn't exist currently. Okay, so that's the takeaway from the technology side. We need intelligent memory controllers that can avoid many failures and enable better scaling. And then the next step is, of course, we can use these intelligent controllers for better performance and energy efficiency. Now, let me go into the systems perspective. Let's jump into the higher level. So today we have 3 major bottlenecks: data access, energy, data movement energy. And you can see that all of them are about energy in the end. And here I borrow some slides that I liked from Valco's presentations in the past. But basically, the key question in my mind is, do we want a world that looks like this going into the future, like the beautiful parts of Montenegro? Or do we want a world that looks like this, like old Pittsburgh? I believe that we want this one, but we don't want the, we want to set high performance also. Basically, we want high performance, energy efficiency, and sustainability all at the same time. We're greedy as humans. Right? because we have a lot of problems to solve. That's why you want the high performance as well. So basically, the problem is our current design principles will cause great energy waste because we're moving data all around the system, as I showed you. They also cause great performance loss, but we don't quite realize it in the sense that we design these machines that are extremely powerful. They add a lot of complexity to our systems, like heavy out-of-order execution, heavy multi-threading, many levels of caching I showed you earlier, right? And prefetching, etc. All these mechanisms are there to actually improve the performance. They're improving the performance when they can. Usually, they're not very good at improving the performance efficiently. But when they don't work, or when they somewhat work, they actually compound the energy waste. So we're in this vicious cycle where we have energy waste to begin with because we're moving data. We're trying to overcome the performance effects by adding more energy waste to our system. I think we need to break this vicious cycle if you want to be truly energy efficient. And this is the cause of the vicious cycle. Processing of data is far away from the data. And let's go back to the picture that I showed you. Basically, we're very processor-centric. All data is processed in the processor at great system cost and great energy cost in the end. So I'm not the first one to tell this, clearly. This is a beautiful article, one-page article from Dick Sykes. He wrote this in 1990s. This is the memory stupid. This is a play with it's the economy stupid, like US elections were happening at the time. The most important thing is the economy, they said. He was saying the most important thing is memory. And coming from him is important because he's the chief architect of Alpha processors. Alpha processors were competing with Intel at the time. They were the flagship processors. They said basically, we designed this Alpha architecture. Our goal was to improve performance. And this beautiful architecture that we designed is capable of finishing 4 instructions every clock cycle. But unfortunately, on this important data-intensive workload, it's finishing 1 instruction every 5 clock cycles, meaning it's operating at only 1/20 or 5% of its peak bandwidth. Why? It's waiting for data to come back from memory, even though it has a huge cache hierarchy. Basically, he says, I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. And I agree with them. Okay, but the processor-centric paradigm is tough to break out of. This is my data for my own PhD thesis. We worked together with Intel, and we basically showed that, this is around 2001, 2002. We basically showed that on the important workloads Intel used to design its processors with, most of the time the processor is waiting for data to come back from memory. And if you're interested, you can read the paper, etc. I'm not going to bore you with that. Okay, you don't believe Dick Sykes, you don't believe me, since everybody believes Google today. Google published this data in 2015. They basically showed the same thing. And according to that, this is all of their data center workloads. You can see the video, search, indexing, Gmail, etc. But basically, on the flagship processor that they use in their data centers, the processor is waiting for data most of the time. So I believe these are actually evidence that we're doing something wrong in our systems. Okay, that's performance. Let's take a look at energy. If you look at energy, these are some relatively old numbers. I borrowed this from chief scientist of NVIDIA, Bill Daly. Basically, this is a double precision floating point arithmetic operation. A complex arithmetic operation is 20 picojoules. This is a memory read or write, 16 nanojoules. You can see that the difference is 800x. Okay, 800x, maybe you can optimize it, but basically 2 to 3 orders of magnitude difference exists between the energy consumption of a memory access versus the energy consumption of a complex edition. So the question is, does it really make sense to bring the data at all to the processor chip to do a very energy simple operation? And while doing so, consume a lot of energy because of that data movement. I believe that it doesn't make sense. And if you actually do the calculations, in order to amortize the cost of this energy, you need to have a lot of reuse on the data because existing processors reuse the data on chip caches. If you don't have thousands of times reuse of data in the system, you're not going to overcome the energy loss. Okay, so let me paint an even more bleak picture. That was an expensive arithmetic operation, I would say. A cheaper one, a 32-bit edition, it's not the cheapest one, is 6,400 times less energy efficient than a memory access. So a memory access is very costly today. So we should really be thinking, how do we get rid of memory accesses? That's why we see these pictures in real life. Basically, more than 60% of the total system energy is spent on data movement, and more than 90% of the total system energy is spent on memory and machine learning. So I would argue that we do not want to move data. We need to shift to a paradigm where we can enable computation with minimal data movement. We want to compute where it makes sense, where data resides, and we want to make computing architectures more data-centric. So clearly, this is a huge task. In fact, this is the picture that I normally use. So you design your memory and storage, and you put your important applications over here, and then the processor asks the question, memory, can you execute this for me? And if so, please execute it and return the result. you can actually think of all of the system as accelerators. And this could be a distributed system of accelerators. Even this should be an accelerator going forward. So even the central processing unit, the idea of central processing unit goes against data-centric paradigms, in my opinion. Everything should be an accelerator, accelerating data processing in the world. Why do we have a central processing unit? Because what's the importance of it going into the future, right? But I'm not going even that aggressively. I'm saying memory is an accelerator. Let's take a look at that first. So there are many questions dealing with this. How do you define the memory and storage engines that are compute capable? How do you design the processor and communication units? How do you design the software and hardware interfaces to enable this? Unfortunately, we don't have very good interfaces today. How do you design system software, compilers, and languages, programming languages? And then how do you also take advantage of how do you rethink your algorithms such that they fit this paradigm over here? And I also mentioned theoretical foundation. I'm going to mention that because it's really important and there's very, very little work in this area. So you can see that this is an across the stack problem, algorithms for devices. We really need to do research across the stack. We're doing some of it and there's some others happening. I should mention theoretical foundations over here because it's important. So if you think about the history of computation, whenever you think about the algorithmic complexity of the algorithms you design, you count operations. How many operations does this algorithm need? And people think, okay, the number of operations correlates with performance or energy. What I just showed you breaks that, right? What I just showed you says that data is the most important thing. And we need a more data-centric theory of computation as opposed to processor-centric theory. And I think going forward, we need to do that. We don't have that yet. Okay, so if you're interested, there's a lot more that we have been writing on processing in memory. And we also have processing in memory courses, and we've been actually covering a lot of these. Clearly, I cannot cover all of these. We have been having tutorials on processing in memory, and this one is upcoming at ISCA next week or the week after. But I should also mention that we need to think differently from past approaches. Here we go into a little bit more technical detail. How much time do we have?
10 minutes is okay.
Okay, yeah, good. I didn't want to go into a whole lot of technical detail, but I'm going to go into a little bit technical detail to show you what's possible. So basically, I believe we need to think differently. We need to enable computation all over the place, but I'm going to focus a little bit more on memory today. So memory is interesting because a lot of our data is already in memory. And previous work did not categorize processing in memory extremely well, in my opinion. In my opinion, there are only two types of processing in memory. So you have processor today and memory today. One option is the processor consists of some, it could be CPU, GPU, FPGA, some sort of machine learning accelerator. Pick your favorite one or pick a combination of them, which is what's happening today. Get it closer and closer. So processing near memory is shorter term. That's why I'm not going to talk about it as much. Let me put it that way. But processing near memory is get the processing logic closer and closer and closer to memory. At some point, integrated with memory. It could be 3D stack technology. It could be inside the memory chip. And this is what's happening in industry today. So we've been proposing it 10 years ago. Industry is finally doing it, which is great. This reduces the distance between memory and processor, and also it enables you to specialize the processor, and it gives you a lot of benefits. So our work has shown that you can actually increase performance and energy both by about 2 orders of magnitude in the end, collectively in the last 10 years. Processing using memory is fundamentally different. You have processor today, memory today. Forget about the processor. Forget about logic as we know it. This memory device, somebody designed it as memory. But fundamentally, this memory has operational properties, analog operational properties, that can actually do computation as well, or data movement, as I will show. So you can think of the memory device as not just a memory device, but a computation device too. And how do we exploit that computation capability inside the memory device becomes extremely interesting, in my opinion. This is something that people have not considered in the 1960s. This has been considered more recently, in my opinion, like in the 2010s or so. So I can talk about this or this. Maybe I'll ask the audience right now. Which one do you want me to talk about? This is longer term, more aggressive. This is shorter term, already happening.
Oh,
First one, okay. Okay. Okay, so let me go with the first one. There's a lot to talk about even with the first one, but we're going to think about memory as an accelerator. So we're going to add some specialized capability inside the memory, but we're going to exploit the fundamental operating principles of the memory structures. We're not going to add logic in that sense. And the interesting thing is, today we're building a lot of accelerators over here, and all of them are processor-centric. All of them are sitting on the left side of the memory bus. Why don't we actually put some accelerators on the memory side over here? Okay, so let me start with a simple thing. Of course, if you think about this, it's always good to start with simple things so that you can actually see what you can do with simple things. If you cannot do the simple thing, perhaps you cannot do more difficult thing also. I'm going to start with data copy initialization. So this is a lot of applications. Whenever you start a process, for example, you copy a lot of data. If you have 10 terabytes of database, you initialize the database first, and it wastes a lot of time and energy. In fact, Google, in that paper that I mentioned earlier, showed that 5% of their cycles, execution cycles, in their entire data set is spent only on these two function calls that do copying and memory movements. This is fascinating. I think 5% is a very large number, averaged across thousands of workloads that are executing the data set. So how do we do memory copy today? So if you want to copy this page, this piece of memory, this piece of memory, let's say 4 kilobytes, which is the size of a page in many systems today, you have to go through the processor. Basically, you go through the processor to actually byte by bytes, copy the data over here, and then byte by byte write the data back eventually. So this is very energy inefficient. So if you actually show this picture to a 10-year-old child, I'm going to test it with my child when he becomes 10 years old. I'm going to ask him the question, how do you do this? Maybe they will tell you, why don't you just do it this way? Isn't it simpler and smarter? That's what we're arguing for, basically, what a child would do, probably. Basically, the idea is this is low latency because you don't go through the processor. This is low bandwidth utilization because you don't exercise a lot over here. It's really called pollution in all of these structures so that you can actually use this for something else more important that actually needs it. And no unwanted data movement over here. Essentially, I'm going to give you a mechanism that takes a 4 kilobyte copy from 1000 nanoseconds to 90 nanoseconds and 3.6 microjoules to 0.04 microjoules. And if you optimize it, it becomes better. So the idea is very simple. This is now going into a little more technical detail. I showed you the rows of DRAM. So most of them already exist actually. So you activate one row. So if you want to copy this row to another row, you first apply high voltage to this row, activate it, which brings the data into the sensing structures in the DRAM. This is called a row buffer. And then you do another activate consecutively, which brings the data from here to here. That's the idea, basically. 2 consecutive activates in a modern DRAM chip, negligible hardware cost if you want to do it reliably, and you get more than an order of magnitude latency reduction and more than close to 2 orders of magnitude energy reduction if you optimize. So this simple idea, I think, has a lot of benefits. We published it, and people are actually doing some similar things, but I think they should be doing more. So the interesting thing is, when we published it, we said you need to modify the DRAM chip slightly to do this reliably. Later work showed that you can actually do this in real DRAM chips. So DRAM chips are not designed to do this. Manufacturers don't tell you that you can do this. But if you actually take this chip and put it into an FPGA-based infrastructure that we developed, these folks from Princeton did that, they basically violated the timing parameters such that they could mimic these 2 consecutive activates that I showed you. And they basically showed that you can actually do this in real DRAM chips. So even though the chip is not designed to do this, you can actually do this. That's fascinating, right? That showed that these principles are already there. And we actually built on their work. We designed a reconfigurable architecture-based framework so that we can actually enable this. If people are interested, they can develop it. So we actually showed this in real systems. That's fascinating. And in real systems, the performance improvements are even larger, as you can see, because you get rid of a lot of the software and hardware inefficiencies. So again, there's a lot of detail over here that I'm glossing over. You can read the paper, etc. But let me give you a few more things. So you say data copy initialization is great, but what about computation? So you can actually do computation as well. So basically, you can have and or not and majority functions in the end. I'll give you the basic idea using the analog computation capability by activating multiple rows. So you get significant performance energy improvements, and this is reported in this paper. There are new memory technologies that enable even more opportunities, like matrix vector multiplication. Let me give you the idea of DRAM. This is fascinating in my opinion. If you look at DRAM, it consists of rows, as I showed you. This is 1 bit per row. But imagine a row is 8 kilobytes or 4 kilobytes. You can do this on 8 kilobytes at a given time. And if you actually have thousands of these subarrays in DRAM, you can actually do this on millions of bits at a time. The idea is to activate these 3 rows concurrently. Now, if you know some circuits, you will see that you connect these to the bit line. And if 2 of these cells are charged, in the end, you get the charge state. If 2 of these cells are discharged, you get the discharge state. Meaning this is a bitwise majority function. So by doing triple row activation, you get a bitwise majority function in here. This is a theory. And then bitwise majority, if you set C to 1, you get OR of A and B and AND of A. Now you have bitwise AND, bitwise OR, bitwise majority. Not is a bit harder, you need to take the complement. So it already exists actually. The complement of the value already exists, you need to actually put it somewhere. So basically, you can have a functionally complete system. Essentially, if you have AND or not, or majority or not, or none or not, that's a functionally complete system. Now you can actually do anything in the system. You just need to rethink your algorithm such that it matches these bitwise majority-based computation. We call this bulk bitwise computation. So there are bulk bitwise operations that you can do in the system. So before I move on to the benefits of this, I should say that in our paper, we said that this is in theory possible. Later work that I showed you, compute DRAM work, showed that in some subset of DRAM chips, you can actually do this by violating the timing parameters. So you get this analog result correctly in a fraction of the DRAM chips. So even though the DRAM chip is not designed for this, you can actually do computation in some DRAM chips today because of these fundamental principles. That's fascinating, right? Imagine what you can do if you actually rethink the chip such that you want to maximize its computation capability in addition to the memory capability. That's what we're working towards going into the future. But let me give you some results. So there are a bunch of applications that are already designed to do bulk bitwise operations, databases, for example, or web search from Microsoft, and a bunch of other things over here that I said. We took a database that's designed for this purpose, and we actually ported it to our system, and we see more than 4x to 12x performance improvements. And these are with small data sets. With large data sets, improvements actually grow. And the energy efficiency is similar. I don't plot it over here, but you get similar energy efficiency. So you can improve both performance and energy at the same time with this sort of processing. Okay, if you're interested, there's a lot more detail in the paper, and we actually have been writing more papers on this topic. We are working on making it programmable, but we don't have a whole lot of time, so I'm going to skip this one. So how do you make this programmable is interesting, and we're working on the programmability issues. And you can actually do much better with better programmable systems. So how do you do complex operations? You may actually have questions. Okay, and or not is good, but multiplication, division, trigonometric functions, how do you do those? You can actually do those with some more changes in DM, and these are more recent papers. You can also do it with what I just suggested, but it takes a bit longer. And also you can have security support in DM. I should also mention this because once you actually move the data or do processing near data, you should also have security functions on the data because you need to securely process data. So we have mechanisms for doing security functions inside DM, like generating true random numbers, for example, which is also quite fascinating. Because again, these are not behavior that's documented by manufacturers. By violating the timing parameters, you get some cells randomly failing. And this is true random numbers because these cells fail because of some true physical phenomenon. And as a result, you can use these cells to generate a bigger random number that could be useful for many, many workloads and many, many security applications. Again, there's more work in this area that I'm not going to talk about. Okay, I think we don't have a whole lot of time, but let me give a concluding slide if you don't mind. Or maybe let me finish it with the concluding slide. As I said, I have lots of slides, but I didn't intend to cover all of them.
We're just missing.
Yeah. But I mean, I usually use the same slide deck, but we configure it. I follow the same principles in my talk also. Okay, so I don't know what is this doing here for me. Okay, so basically, I think going forward, we must design systems to be balanced, high performance, and energy efficient. We need systems to be data-centric, data-driven, and data-aware. We talked a lot about data-centric, which requires enabling computation capability inside and close to memory structure. That's actually everywhere, I would say. This can lead to orders of magnitude improvements, enable new applications and computing platforms. I didn't discuss this, but I think genome analysis can be enabled with new computing platforms using this sort of technology. Enable a better understanding of nature. Actually, this is very interesting because, as mentioned earlier, I was studying psychology and computer engineering at a time when psychologists were thinking, oh, we can explain the nature based on the principles of computation. Basically, computers were a paradigm for explaining psychological behavior. They forgot about that because it didn't work. Computers have nothing to do with how humans operate. But I think this sort of computation is actually different. Essentially, it's more closer to nature, as I will show you in a little bit. So who knows what else we can enable? So I believe the future of truly memory-centric computing is bright because fundamentally it enables all of these things. I believe it enables security also. But we do need to do the research and design across the computing stack. So I will maybe leave you with this picture. So if you look at this computing device, I believe it's a computing device, and you can also question that, of course. Is this computing device in any way similar to the principle that we use in our computer systems today? We're getting there, but the fundamental thing that we do on our computing systems, being processor-centric, is nowhere close to what this does. As far as we know, and we don't know enough, in my opinion, as far as we know, this is much more data-centric. Computation, communication, and storage are more coupled inside. Much more data-driven, clearly. It has some substrate that can learn over time through some sort of connectivity. And much more data-aware. there are specialized sections that are aware of different types of data over here. So I think we need to learn a little bit more from here. But if we get closer to the design principle that is used in this thing, maybe we can actually do better in terms of understanding this thing also. Okay, I will conclude with the slide. I'm happy to take any questions.
I will abuse my position to ask a couple of questions. As far as I understand, the same problem with the memory-centric or not memory-centric computing exists for these GPU architectures, and it means that we are wasting a lot of money here by, let's say, $10,000 nodes in that case.
Absolutely. Yeah, so GPUs are another example of a processor-centric system because they're far away from memory. And you need to bring the data into, let's say, an array of computing units that are far away from memory.
The second question is, I'm a little bit, I would say, worried. It took some time that I'm teaching students in computer languages. And it took some time that the community accepted corporate program, and that we have some kind of standard of what will happen with this kind of memory-centric computing? What do you expect in that?
So that's a great question. So this is something that we are tackling and our community is tackling also. What is the right programming paradigm for this? How do we integrate it? I don't believe we have the answer yet. There are a lot of, let's say, competitors, meaning how do we integrate this into a programming language that can really take advantage of it? So in some of the slides that I didn't show, we actually completely redesigned the system such that you have a message passing based programming language that take advantage of it. Is that the right thing to do? We don't know yet. That's what's happening in machine learning accelerators today. So there's actually some tendency, these specialized systems that people are building that are compute-centric, some of those programming systems can be used for memory-centric computation also. But you do need to think a little bit differently because now you don't have a central processor. So I don't have a perfect answer for you, unfortunately. There are also ways of integrating some of these memory operations to the compute-centric programming languages. You don't get a lot, most of the benefit. You get some of the benefit. So that's one way forward to make it easier to program. But I believe the jury is still out. We need to figure out how to program these things. And also, we need to also work on the compiler stack to enable compilation of these systems. If you ask me the question, like the GPUs, for example, were similar 20, 25 years ago, right? People didn't know how to program them, take advantage of them. Over time, this developed, and NVIDIA had a great idea of this CUDA, and they commercialized it clearly. So I believe something like that needs to happen in memory-centric systems also. Over time, we'll need to figure out how to program these.
Is there any other question?
First, I thank you very much for this interesting and inspiring presentation. It was really interesting to hear what are directions of computation. I'm interested in one of the direction is moving the calculation to the memory, so that memory does some of this, we've seen simple operations. So I think that will now become more and more complex, and computation related to the memory chips and memory will be more complex. So it will go toward having a CPU in each of memory blocks. What will be the difference of that CPU standard one and calculation unit that will be attached to the memory, because it has to be specific, not to mimic the central CPU?
That's right. So that's a great question, basically. What are the characteristics of the CPU or logic that you put inside the memory chip? We're exploring still, but what you cannot do easily on the memory side is extremely complex, extremely high frequency operations, because the fundamental fabrication technology is different. In DRAM, flash, all memories we know of are, at least large memories, are different from the technology that we use to build efficient transistors on CPU. So you cannot, in general, have a very high frequency and very complicated logic. Of course, you can do it with extremely high cost, right? But we don't want high cost also. So this CPU will still not be that powerful, in my opinion. going into the future compared to the central processing unit. So in my opinion, central processing unit will never be eliminated. There is a need for these extremely high performance processors, but they should be doing what they're really good at doing, which is just computation tasks that are not done by memory. So this other CPU over here, a little bit weaker, etc., it will be used for tasks that are much more data moment intensive, like simple processing tasks on the data. Over time, they will become more complicated, in my opinion, as we figure out how to make them more complicated. But initially, I think there needs to be a division. So there's still some room, a lot of room for these compute-centric CPUs.
I will just continue on this one. CPU looks like it will never be replaced. Like the man will be never replaced in the artificial intelligence. So we can do that kind of parallelism.
So I think maybe, but I'm not. But the question is, what does replacing mean? In my opinion, CPU will become yet another accelerator over time. So right now we say we offload computation to a machine learning accelerator. We offload computation to a GPU accelerator. GPU is still considered an accelerator. We offload computation to a memory-centric accelerator. Over time, CPU, in my opinion, will be called a compute-centric accelerator. Essentially, it will have its tasks that it's good at, and everybody else will have their tasks that they're good at. Do you really need a central processing unit at that point? Then it is a question of software in the end. How do you design your software? If it's really centralized, then you probably need a central processing unit. But if your software also becomes distributed, then all of them will be coordinating agents that work with each other. But of course, this is more of a fundamental thinking, in my opinion. Industry will require decades to adapt to this, in my opinion. You're welcome.
Wait for the last question.
So, maybe could you comment a bit more about the configurable hardware adapting autonomously to different data processes? That's a great idea. The question is how to make it adaptable autonomously to different data processes.
Yeah, that's a great question. I mean, I don't know. I should say I don't know the answer to that question. That's part of what we're also trying to examine. But I'll give you our experience. So, for example, we have designed memory controllers that use reinforcement learning principles to adapt their scheduling policy to the properties of the data that's flowing. We have designed prefetchers that also use reinforcement learning principles. So I think using some principles from machine learning, reinforcement learning, is helpful to adapt your policy to the types of data or types of access patterns, for example, you're seeing. So we have limited experience with that, and we see significant benefits from that perspective. But I think your question is even broader in the sense that how do you enable generally configurable hardware to reconfigure itself, for example? I don't know if there's any conclusion on that, but I think that's a great stretch.
That if we have to move something, we move what is left. If a program is big, a data is huge, we move data to the program. If the program is well, the way it is, but the data are huge, then we move the program to the data. But actually, everything here in this game is not as simple. There is an important thing to ask to. So, what is that important thing to estimate the risk?
Basically, figure out how to do this or how to partition it. I see. Yeah. So that's something we've been working on, basically, how to decide where computation should be done. And you need some sort of methodology and runtime system that enables the decision, essentially. That's what we've been, on the slide I skipped, for example, there was a paper where we actually analyze the bottlenecks and analyze when you should move the data to computation and when you should move the computation to data. It's not as simple, unfortunately. You need to do a lot of trade-off analysis on this one, but I believe runtime systems that enable that decision-making, partially with reinforcement learning or some sort of learning mechanism, is going to be useful for that decision-making.
Thank you very much.
Thank you.
It was very, very great presentation. I hope that you are ready to stay here in Montenegro and continue the same way and the other great presentations that you have here. That's your attraction. Thank you very much.
Thank you.